Good evening. It's Sunday evening, and I'm doing a stream today about Mealy and a little bit about More Machines. It's kind of a recap of what we did on Thursday in class, where we talked about Mealy and More Machines. And so there was a request for me to do a stream and maybe clear up some of the questions that came up during the class. So I'm just going to kind of go over the same examples that we did in class, and just by having it maybe gone over again, it might clear up some of the questions that you had. All right, so, well, the first thing is to talk more generally about what these things are. In the past couple of weeks, or also in the past couple of videos, we talked about deterministic finite state machines and non-deterministic ones, but the outputs of those machines has always just been a yes or a no. Or another way to say it is like an accept or reject. So either the string is accepted or the string is rejected, just a binary 1 or 0. The idea behind a Mealy and a More machine is it's still a finite state machine, but now the output of it is a string rather than just simply a yes or a no. So let me kind of show you a quick example here. So I've got a bunch of dots here on the screen, and maybe the first question I could ask is the number of dots I have on the screen even or odd? Now, if you're thinking like a programmer, what you'll probably do is count up all the dots and then do something like divide by 2 and see if the remainder is 0 or 1. If the remainder is 0, then you've got an even number, and if you've got a remainder of 1, then you've got an odd number. So that's a perfectly good solution, but we can actually do the same thing with a deterministic finite state machine rather than some kind of variable that's keeping a count and then dividing by 2 at the end. All you really need to do is have some kind of flag, like a Boolean flag that just flips back and forth between even and odd. And so as you pick up as you count one of the dots, you flip that flag to either even or odd, depending upon which you're on. So, for example, if I was to look at this one first, I would say, okay, I have an odd number of dots so far, and now I've got an even and an odd, even, odd, even, odd, even, odd, even, odd. As I go through all of the dots, eventually I'll come out at the end with an answer. It's either even or odd. And so that sounds kind of like a standard DFA or NFA that gives you a yes or no answer. But what we're going to do is kind of introduce the idea that this machine is going to produce a stream of output. And as it goes along, it's going to go even, odd, even, odd, even, odd, even, odd. And at the very end, the very last symbol it outputs is the answer you want. So let's look at what that machine would look like. It does kind of look like a DFA. It's got a start state, but it usually doesn't have an accepting state. So here's our start, and there's going to be a couple of transitions here. So let's use as the input to this a single dot. So there's a dot of some sort. And the first time we encounter a dot, that is the first time we make this transition over here, that means we've seen an odd number of dots so far. So our output will be odd, or let's just say O. And then the second time we see a dot, second time we count one, so if we go from here to here, then we've seen an even number of dots. So if we see another dot, we're going to output even, let's just say E. Okay, so that means, I didn't count how many dots are on the screen here, but let's say there's 37 dots on the screen. So if there's 37 dots, it means we'll start here and we'll go around and around and around and around and outputting an O or an E every time we make one of these transitions. So the output of this machine is going to be O, E, O, E, O, E, O, E, and it's going to keep going. And finally, the very last one it outputs is going to be O, because I said there's going to be 37 dots on the screen. And so this answer right here would be the one we're looking for. So that's just counting whether there's an even or odd number of dots. But now if I change the question a bit and I say, is there, let's say, an even or odd number of the purple dots, which are these here, this one and this one and this one. So I want to be able to go through all the dots, but determine if there's an even or an odd number of the purple ones. So that state machine looks a little bit different. Still got two states. that are accepting here. But now, if we see a purple, we'll output an O. If we see another purple, we'll output an E. And then if we see anything else, we should output something. So if we're in the first state here, and we see, let's say, a green dot, we haven't changed the number of purple dots we've seen, so it should output an even, and this one here should output, let me not put even, let's just put E, this should put O, okay? So let's say we see, well, so now what we can do is we can actually put in like a input stream. Now, instead of saying purple, green, or blue, I'm just going to use P, G, and B. So let's say our input stream is P, G, P, P, B, G, G, P, B, G, P, B, B, G. Okay, so that's our stream of symbols coming in representing the dots as we're counting them. So as we go across here, we're going to output O, O, E, O, 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 O. I've lost my track. Oh boy, I lost track. I better write this down. So the first time we see a P, we're going to output O because we've now seen an odd number of purples. Then if we see a green, we're still going to output O because we've seen an odd number of purples. Then an even number, then an odd number, odd, 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 even, 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 odd, 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 odd. So basically every time we see a purple, we flop that flag back and forth. So at the very end, the last symbol that we output is an O, indicating we've seen an odd number of purples. Okay, so I see on my window here that 5 people are watching. This is an all-time record. If you are watching on the desktop version of YouTube, then you can join in the chat. There's a sidebar that you can type in. However, if you're watching on a mobile device, I've heard that chat window does not show up. So if you do want to ask a question, go ahead and bring it up on your desktop version, or let us know if, in fact, you can see the chat window on the mobile version, like on your phone or a tablet. All right, so I think that kind of covers the idea of the even and odd. So let's look a little bit about how the Mealy machine is constructed. So it is just like a standard finite state machine with states and transitions. And we do have inputs on the transitions. These inputs represent the symbols coming in, the string that we're trying to produce an output for. But we've got this additional piece here, which is every time you make one of those transitions, you also output something. So rather than outputting a yes or no at the very end, you output as you're going along. So you can see here, every time we encounter a purple, we're going to output an O or an an O or an E. If we encounter something else like a green or a blue, then we output something else like an O here or an E here. So the slash is used to separate the input from the output. And I see now that my drawing needs a little loop just to complete it. There we go. So the Mealy machine looks like a DFA or an NFA, except that it also has an output associated with every input, every transition. All right, so let's go on and do another example. This one is to take a binary string and invert all the bits. So turn all the zeros into ones and all the ones into zeros. So kind of the idea behind introducing these Mealy and Moore machines is to abstract away from this idea that binary numbers are numbers, which we've been kind of insisting all semester, And instead of them being a number, like a base 2 number, now what they are is a string of symbols, which are a string of digits, a string of ones and zeros. And all we're doing is manipulating that string. We're not doing something like convert the number into base 10 or base 16 and then do operations on it. We're just considering it as though they're just a string of ones and zeros, and we're not really looking at the value of the overall number. So when we say something like invert bits, we're not talking about the classical sense of like applying the not operation to the 1 or the 0 to flip it around to its opposite sign or opposite value. What we're doing is just looking at the symbol. Is it a 0 or a 1, and doing something to it. So you know what inverting bits means. It means like take a binary string like that and turn it into 1 0 0 1 1 0. Just basically flip all the bits. So this can be done fairly simply. Every time you see a 0, you output a 1. And every time you output a 1, you output a 0. So it looks something like this. That's all it is. So, if we go through this string, either from the left or from the right, every time we see a 0, we output a 1. Every time we output a 1, see a 1, we output a 0. So it works either way on this one. That one's like really easy. Maybe a more complex example would be add 1. Okay, so now a couple of weeks ago, I told you that finite state machines can't do anything like count. For example, since finite state machines are equivalent to regular expressions, there's no way to construct a regular expression that could, say, count the number of the letter X in an input, or do something like match parentheses, make sure that for every opening parentheses, there's a closing parentheses. Regular expressions can't do that because they have no form of a sort of a general purpose memory. I mean, they can remember, you can encode states to remember specific things like I saw a parentheses, but you can't do anything like I saw n parentheses, I saw n open parentheses, and so therefore I need to see n closing parentheses. You can encode a state to say like I've seen 3 opening parentheses, and then I need to match it up with 3 closing parentheses, but you can't generalize it to be any number. So when I say that regular expressions and finite state machines can't count, it comes as some surprise to say like, well, actually, they can add 1, or they can add any. Well, as we see, like if you can add 1, well, that means you could add 2, right? Because just kind of run 2 of them together. You could add 1 and then add 1 again, but you can't do like an add n, or can you? Well, let's find out. So add 1 would be, let's say if we have 0 1 1 0 0 1 0, and then we were to add 1 to this. Well, the output's easy, right? You just look at this column at a time, and you go 0 plus 1 is 1, and then the rest is the same because there's no carry from that operation. So this add 1 operation always goes from the right-hand side, just like you do in regular longhand addition. If we do another one here, 0 1 1 0 0 1 1. This time I've just got 2 ones there on the right-hand side, and we're going to add 1 to that. Now, when we add 1 and 1 together, we get 0 from that, and there's a carry. And then 1 plus 1 is 0 again, and there's a carry. And then there's a 1 plus 0 is 1. And at this point, there's no more carries to do, so the rest is the same. Let me do that with just a whole bunch of zeros. If I add 1, then 0 plus 1 is 1, and then there's no carry from that, so the rest is the same. And so if you do enough of these, let's say 0 1 0 0 0 0, 0 plus 1 is 1, and then the rest is the same. Okay, and then maybe, I think that's enough there. I think if you kind of, what you have to do is do enough examples so that you can see what's going on here. And if you really analyze, don't think about it in terms of a binary number, just look in terms of ones and zeros. If you look at this rightmost column, the least significant bit column, you can see that the output of this 1 down here, compared to the input, it's always the opposite. So this 0 over here, if it's a 0 in the rightmost column, it becomes a 1. If it's a 1, it becomes a 0. That's sort of the essence of adding 1, is you're always going to flip the value of the least significant bit, the rightmost bit. So that sort of leads to this idea that there needs to be a state to represent what happens in that rightmost position. Either we get a 0 and it becomes a 1, or we get a 1 and it becomes a 0. So the rightmost bit always flips. But then what happens to the rest of the number? Well, what we can see here is that there's sort of two phases that the number goes through. There's this phase where you get a bunch of carries, and the carries cause the numbers to flip each time. So if there's a carry, it flips values. And if there's no carry, they stay the same. So I see, and this is sort of my first pass at this, is that there's three phases that the string goes through. The first one is to flip the rightmost bit. The second one is to handle the carry that's going through. So as long as there's a carry, you're going to flip the bits. And then as soon as you're done with the carry, you're going to go into this third phase where you're just copying the bits. So you're going to do a flip on the first one. You're going to do a flip for the carry positions, and then you're going to do a copy for the remaining ones. So again, this is sort of first pass at it. We'll see in a moment here that there's actually a way to optimize this one here. But so here's our start state. Let me move it down a bit. Nope. Where can I do this? I guess I'll do it up here in the corner, and I'll just draw this line to say we are not going past this line here. There we go. All right, so we've got this start state here. And then, let's see, the way I'm going to do it here is if the first bit that you see, or the first symbol that you see, is a 0, then you're going to output a 1. And then you're going to go into this phase where you're starting to do a carry, right? Because, I'm sorry, is that right? If there's a 0, there's a 1. Then see, what we're doing there is there's no carry, okay? And then if you see a 1 first, then you're going into this phase where there is a carry. So that handles which situation? This one here. So if you see a 1, then you should output a 0, and then you're going into this carry phase where you're flipping the bits. So I'll label this the carry, and I think I want to label it up here. No, I'll label it later when I see how this is going to come out. So that means when we're in the carry phase, as long as we see a 1, we should output a 0. So as long as we continue to see 1s, we know that we're going to keep propagating a carry through. And so we're going to stay in that state. But then, once we're all done with that, as soon as we see a 0, we'll again output a 1 because there was a carry to handle, and that is this one here, right here. So as soon as we see a 0, we're going to output a 1, but now we're going to go into this phase where we're just copying the bits. And so that means if we see a 0, we output a 0, and if we see a 1, we output a 1. Okay, so this is the carry, this is copy, and this is the least significant bit over here. Okay, and I realize now that the way I have my screen cropped, Unfortunately, you can't necessarily see the bottom of the screen, and I apologize on the previous screen where I had all those dots on the screen, and you probably couldn't see what was at the very bottom. So what I'm going to do is I'm going to transfer what I had at the very bottom of the screen right above it. And then I got to remember not to draw below a certain point on my screen. This is a new way for me to crop the screen today, so I apologize. So let me bring out some of this stuff here. Let's see if I can do this. Yep, okay, and then I'll have to move out of the way. Okay, so I moved the string up above it. And that should take care of that. Okay, and then let me go now to the second screen. And I'm sorry also there was a skip in the video there. Another problem I need to solve. Okay, so now you've got all the symbols up above there. I've switched over to the other screen, and we're back to the Mealy machine that handles adding 1. So as I said before, there are 3 states. There's a first state that handles the least significant bit, and then there's 2 other states that either copy the remainder of the bits or they invert the remainder of the bits. Okay, so I guess what we could do is we could talk about now optimizing this, because we actually don't need this first state here, because you can kind of think of adding 1 not as this separate operation you're doing, but as actually passing in a carry of 1 up here, right? So instead of this second row consisting of the 1 down here, think of there as being an implicit carry that's coming in from some unseen bit off the right-hand side. So there's essentially like a 1 over here. So that means there's actually a carry on the first bit, and then the remainder of the number is either going to be a carry or a copy. So that means we can get rid of this first state here and instead start in this one here, start in the carry position. So if we see a 1, we output a 0. If we see a 0, we output a 1, and then we go back into the copy phase. So what we'll end up with is, and what I'm going to do is I'm just going to kind of cross it out by highlighting it and saying, we don't need that stuff there. Don't need. And then you actually start in the carry state. And then that machine there should add 1 to any binary number. So let's try it out. So if we do, let's say, this one over here, we start at a 0, which is we start in this state here. And if we see a 0, we're going to output a 1, which is this one here. And then from that point forward, we're just copying the bits. And by forward, I mean to the left. 1, 0, 0, 1, 1, 0. It's just going to stay in this state over here. Let's try this next one over here. If we see a 1 here, we're going to output a 0, which is this one. And then if we see another 1, we'll output a 0. If we see a 0, we're going to output a 1, and then we go into the copy state. For this one over here, if we see a 0, we're going to output a 1, which is right here. And then we go into the copy state where we do the rest. Okay, and that handles the last number over here on the right-hand side as well. Okay, so that's the idea of making a Mealy machine that will add 1 to a... Now again, I want to be careful and not say a binary number. I want to say it's a binary string, so it's just a string of 0s and 1s. But now if you can invert bits, invert a binary string, and if you can add 1 to a binary string, it kind of tells you that you ought to be able to do 2's complement. And certainly you can. You can just make 2 of these machines. You can make one machine that inverts all the bits, and then the output of that gets fed into the next one where it adds 1, and then you've got yourself 2's complement. But there's actually a different way to do 2's complement, and this is the way that a computer actually does it. The computer doesn't really flip all the bits and add 1. It actually does this operation. Okay, so, well, first of all, 2's complement. Let's do some examples. Let's say we have the number 0, 1, 0, 1. So that we're trying to find the 2's complement of that number. So the typical way you think about it is invert the bits and then add 1 to it. So you get 1, 1, 0, 1 like that. But I think we can actually make what's going on a little more clear if we do a kind of contrived number with a bunch of zeros over here and a couple of 1s toward the left-hand side. So if we invert the bits, all the zeros become 1s, all the 1s become zeros. We add 1 to it, and then look what happens here. We get 1 plus 1 on the right-hand side. That becomes 0 with a carry. And then we get 1 plus 1 again, so it becomes 0 with a carry, 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 1 and 0. So there's a 1 there. And then at that point, there's no more carry. So we end up with just the same bits coming down. Okay, so now look what happened here. The original number had 6 zeros on the right-hand side, and the 2's complement number also has 6 zeros on the right-hand side. So it looks like the output of the 2's complement operation just has the same number of zeros on the right-hand side. So however many there are on the right-hand side over here, there should be the same number over here. And then if you look at the remaining bits, you can see that the 1 here became a 1 here, and then the 0, 1 here became a 1, 0 down here. So that leads you to the second way of doing 2's complement, which is start from the right-hand side, and as long as you see zeros, just copy them down to your output. As soon as you see the first 1, copy it down to the output, and then from that point forward, just invert everything. Okay, so we'll say it again. You start with, as long as you see zeros, you copy them down. When you see your first 1, you copy that one down, and then you invert the rest. Okay, so that means that you can do this with 2 states. You can do that with the zero, copying the zeros, and then there's a transition to the second state when you see that first 1, and then there's an invert state. So it looks like this. So as long as I see a 0, I'm going to output a 0. And then as soon as I see a 1, I'm going to output a 1, right? So I'm going to copy that 1 down. And then from that point forward, I'm going to invert everything. Yeah, and that's it. So this one here should find the 2's complement of any binary string. Let's try it out with the first one here. So if we start out with a 1, that means we follow this transition first. So we output a 1 right here. And then from that point forward, we just invert all the bits. So the 0, 1, 0 here became a 1, 0, 1, which is what this state does. And then with this example, we have a whole string of zeros, so we end up doing this 6 times. And then as soon as we see a 1, we output a 1, and then we invert over here. And that handles the rest of the string. So that's 2's complement. Okay, but then earlier I said, well, deterministic finite state machines can't add, but actually a Mealy machine can, sort of. But again, it's not looking at numbers, it's just looking at patterns of zeros and ones coming in. So let's take a look at add two binary strings. So let's say we're adding 0, 0, 0, 0 and 1, 0, 1, 0 together. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1. That one's easy. What if we did 0, 1, 1, 0 plus 1, 0, 1, 0? 0 plus 0 on the right-hand side is 0. 1 plus 1 is 0, but there's a carry now. So 1 plus 0 with the carry is 1, and there's another carry. And then 1 plus 0 plus 1 is 0, and there's a carry. And actually, we don't care about what happens on that fifth bit together because we're only just dealing with 4 bits. And this is one thing about like Mealy and Moore machines is that basically the outputting string is the same length as the inputting string. So we're not going to handle moving that carry over to make a fifth column. So on this Mealy machine here, we're not going to have a single bit as its input. It's going to have a pair of numbers where each one of the numbers is one of these columns here. And so we need to handle several states. We need to handle that. We end up with 2 states on this one. There's the adding 2 numbers and there's no carry, and there's adding 2 numbers and there is a carry. So let's see if I can work this out. We got a question, is that third bit from the left correct? Or I mean from the right. You know, I probably made a mistake. Let's see. 1 plus 1, aha, you're right. 1 plus 1 is a 0 with a carry, and then 1 plus 1 is a 0, is that right? With a carry, and then we forget about the fifth one. So we end up with all zeros on that one? Yeah, I guess we're right. All right, so returning to our example, we got 2 states. Here's our start. And let's see, if we do a 0, 0, we should output a 0, and that corresponds to this one here. And if we do a 0 and a 1, whoops, we should output a 0. That corresponds to just adding a 0 and 1 together, and there's no carry, and that would correspond with doing one of these here. And then there's the flip side to that. 1 and a 0 also outputs a 1. Oops, and I see that I made a mistake here. There we go. And then there's the fourth possibility, which takes us over to this other state, which is if we get 2 1s, then we should output a 0. And then we go over to our state where we're handling carrying a 1 through. So notice that we're not actually doing the carry. We're just, by going to another state, representing the fact that we have a carry. So at this point, let's see. If we see a 0, 0, whoops, no. If we see a 0, 1 with a carry, that means we should output a 0 and stay in this carry state because this one generates a carry of its own. And same thing for the opposite. So that one generates a carry as well. And then let's see, if we do a 0, 0, that takes us back to the first state because an input of a 0, 0 with a carry produces a 1, but then that itself doesn't produce a carry, so we end up going back to the first state. And then there's one more to consider, and that's what if we get a 1, 1. So if we get a 1, 1, we output a 1, and there's still a carry. So I think that's it. So I think this Mealy machine here adds 2 binary strings together, and we can try it with this one over here. So if we start here in our starting state and we get a 0, 0, we output a 0. And then if we see a 1, 1, we output a 0 and go over here. So that's this one here. And then if we see a 1, 0, we output a 0 and we stay over here. Then if we see a 0, 1, we output a 0 and stay over here. And then essentially we're done. So I think it works. And then for the left-hand one, if we see a 0, 0, we stay here. If we see a 1, 0, we output a 1. If we see a 0, 0, we output a 0. And if we see a 0, 1, we output a 1, and then we're done. So this one had no carries at all, so it just stayed in this state over here. Okay, so we had a question that says, do all possible transitions have to be accounted for? So could logic say that if it's not 1, 1, then stay here? You know what, I would kind of avoid doing that, simply because when we were doing things like our deterministic finite state machines, I kind of said that any input that's not explicitly listed should go to an implicit error state, which says that the string is not recognized. And so what we want to do here is make sure that we account for all the expected strings that we're going to see. If there's any strings that we don't see that are if there's any strings that are unexpected, like let's say we were, and I'm just hypothetically making an example here, let's say we were adding two binary strings together, but we didn't account for, let's say, a 1, 1 over here, then what should we do? The DFA would say, like, well, that's a string that we didn't expect, so we should go to an error state and say that that string is not accepted. So I think we should list the 1, 1 here to explicitly say we're staying in the same one instead of leaving it kind of vague and ambiguous about what to do. So that would be my answer, which says that any string that you're expecting to see, you should put in your transition diagram. Any string that you're not expecting to see, you could leave it out with the notation or the idea that you're going to go into an error state when that happens. Now, because we're dealing with binary strings here, there's not too many possibilities to consider. Either it's going to be a 1 or a 0 or a pair of 1s or a pair of 0s. And so I think that'll be my answer to that. So really, although a DFA or an NFA can't add 2 numbers together, a Mealy machine can add 2 numbers together. And again, we're not considering it to be a number at all. We're just considering it to be a string of 1s and 0s coming in. And so it does produce the right answer, even though we didn't actually do anything like base 2 conversion. We were just essentially doing long addition like you learned in elementary school. You could actually extend this to do adding 2 decimal numbers, adding 2 base 10 numbers together. You just have a lot more transitions, but you still, I think, only have 2 states. Either you're doing a carry or you're not doing a carry. It's just that you have to consider not 4 possibilities here, but probably 100 of them, right? For every pair of possible numbers you could have here. You'd have to find some way to compress the diagram, say like 0, 0 through, I don't know, whatever ones don't generate a carry, you'll list all of them here, and then you'll list here all the ones that do generate a carry. You'll list here all the ones that continue to generate a carry. You get the idea, right? There's still only 2 states, but you could add any 2 base 10 numbers together using this diagram. All right. How about recognize the substring AB in a longer string? So let's say we have A, B, A, B, B, A, B, A, B. And the output of this is going to be 0 or yes or no. Let's use zeros and ones, but it could be yes or no. 0, 0, 1, because we saw an AB, and then a 0, and then a 1, and then a 0, 0, 1, 0, 1. So every time we see AB in a row, we're going to throw a 1 out. And then by looking at the string, we can very clearly see there are 4 instances of the string AB inside of that larger string. So this is different from a regular expression, which would just give you a yes-no answer. Does the string AB occur somewhere in the string? What this one will do is output a 1 every time there's an AB in there. So the Mealy machine for this looks a lot like a DFA in that we do have to recognize AB. So we start on the left and we go towards the right. And as soon as we see that B, we know we're going to output a 1. And when we see that 0, we know the A, we're going to output a 0 because we haven't seen the AB yet. So when we see the first A, we'll output a 0. And then as soon as we see the B, we're going to output a 1. Okay, but now we have to handle all the other possibilities. So what happens if we're in the first state and we see a B? Well, that means we haven't seen AB yet, so we should output a 0, but it also means we should stay in the same state because this first state over here represents waiting for an A to happen, right? And this second state here represents I saw an A, now I'm waiting for a B to happen. And the third state represents I saw an AB, now I'm going to output a 1. Okay, so the first state here, if we see a B, we should output a 0 and we should stay right there, indicating that we haven't seen an AB yet. And then in the second state here, this is going to be what happens if we see another A? And that's this one right here. So if we see 2 A's in a row, remember the second state here represents I saw an A and I'm waiting for a B. And so here I've seen an A. Actually, this is the second A I've seen. I'm still waiting for a B, so I'm going to stay in that second state right here. All right, so now we've handled A and B out of the first one. We've handled A and B out of the second one. Now we've got to handle A and B out of the third one. And the answer there is if after seeing a B, if we see another B, we pop all the way back to the first one. So if we see 2 B's in a row, we pop all the way back to the first one, which says, I'm done looking at B's. Now I'm waiting for an A again. And that is handled right here. So we see this AB, we output a 1, we see another B, we have to go all the way back to state number 1, the first state, because now we're waiting for an A to come again. And then there's another transition, which is here, a 0, which says if we see a B and then we see another A, we go to the second state because now we've seen an A, right? But we're waiting for a B to happen. So that's kind of handled right here. So as soon as we see a B, it's handled right here. So as soon as we see a B, if we then see an A, we go over here. And then if we see a B again, hey, we can output a 1. Okay. So I think that should handle pretty much all of these. So if we start over here, if I'm working from the left-hand side, if I see an A, I output a 0. If I see another A, I output a 0. Then a B, output a 1. A, output 0. B, output 1. B, output 0. A, 0. B, 1. A, 0. B, 1. Right? So this Mealy machine recognizes as many ABs as appears in a string. Okay, but what if we want to do something a little more complex than that? Let's say we want to recognize let's do AB or BA. So this would be the regular expression, AB or BA. Okay, so let's do A, B, A. The same string. We'll just do the same one. B, B, A, B, A, B. I'll tack on an A on the end. So the output of this should be 0, 0, 1, because now we've seen an AB. And then BA, we should output a 1 for that. And then AB, we should output a 1 there. BB, that's a 0. BA, that's a 1. AB, that's a 1. BA, that's a 1. AB, it's a 1. BA, it's a 1. Right? So every time we see either an EAB or a BA, we should output a 1. This one, I'm going to have to fuddle my way through because I didn't write it down before the stream started. So let's see if we can figure it out. Certainly, if I'm in my initial state and I see an A, I should output a 0 because this is the first thing I've seen. And then if I see a B, I should output a 1. That part seems clear to me. Now, if I am in the first state and I see a B, I'm going to draw that as another one here, another state. And then if I see an A, I'll put a 1. All right, so now I've handled recognizing the two strings, but now I have to put in all the rest of the transitions about like what happens if I see, and if I'm in this state here and I see another A, then I think I got to stay right here. So likewise for this one down here, if I see a B, I'm going to stay here. Okay, now we got to handle the two ending ones. So if I'm in the last one here, I've just seen a B, and now I see an A. That's one of the ones I want to recognize. So I think, well, let's handle this. If I see an A and then a B and then another B, I think I need to go down here. Like that. All right, so if I see A, B, B, then I should output a 1 for that first B and then a 0 for that second B, and then go down to this state here, which represents I've seen a B and I'm expecting an A now. Okay, so that's this one. And then this one over here is going to, I think, cross up to this one here. Oh, sorry, yeah. So if I see another A, I'm going to cross up to this one. Yikes, this is getting complicated. I'm going to have to do this in a different color so you can see it. Like that. And then we got two more to consider. What if I'm in this last state here and then I see an A? So I see an A, B, and then another A. A, B, A. So that means that it was actually kind of like going through this path here. So I should end up down here. A1, because that's a legitimate thing to output for. And then there's going to be another one. Uh-oh, ran out of space again. I'll do it in green. That's this one here. If I see if I see a B, then I'll put a 1. I think that's it. Oh, but there's a simpler way to do it. Yeah. Well, see, what I was doing was just kind of working through all the possibilities in my head. Let's find out a simpler way to do it. So we know of 5 states here. Let's see if we can do it in fewer states. So this is recognize AB or BA. So only considering the right 4 states, the top right and bottom left states can be combined, as well as the top and bottom right. Let me flip back to the other screen. So top right and bottom left. You mean this one and this one? Those can be combined? And top left and bottom right, those can be combined. Well, I think you're going to have to help me out. Okay, so we start here. And I think he's saying there's going to be 3 states. So if we see an A, we'll output a 0. If we see a B, we'll output a 0. And then if we see a B, we output a 1. Is it like this? Let me try it out. A, B, A, B, B, A, B, A, B, A, B. And the output of that should be 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. Let's see if that works. So we start here. A0. Oh, whoops, I'm missing some transitions. Oh. A0. B0. I think that's it. All right, let's try it out. A0, A0, B1, good. A1, B1, B0, A1, A0. Yeah, it's looking good. B1, A1, B1, A1, A0, B1. Great. Yeah, so this can be done with 3 states instead of 5 states. All right, so I think the last thing I'm going to leave you with is just a brief thing about Mealy versus Moore. So with a Mealy machine, outputs go with transitions, and with a Moore machine, outputs go with states. Okay, so a Moore machine, I guess, looks more like a traditional DFA, but every state is associated with an output versus a Mealy machine where the outputs are associated with the transitions. So I'm just going to, sketch something out here. That has no bearing on reality here, or no particular example here. But let's say we have A, B, B. Is that right? No, I'm going to switch one of those. Okay, and here's my start. So the idea here is that I have my transitions, but every time I land on a state, I output what I see there. So if I land on this N state here, I'm going to output an N. If I land on the Y state, I'm going to output a Y. So the main difference between a Mealy and Moore machine here, other than where the outputs go with, also is that as soon as you start, you land on that first state, and so you output something right away. So a Mealy machine doesn't output anything until it's seen the very first symbol at the very least. A Moore machine outputs something right away. So even if you haven't seen any inputs at all, you still see at least one output. But otherwise, they're equivalent. You can convert a Mealy machine into a Moore machine and a Moore machine into a Mealy machine, except for that one little thing there. And so one of the things that a Moore machine kind of can do easier than a Mealy machine is recognize, let's say, a regular expression like well, just, X star, something like that. So 0 or more X's. A Mealy machine has a tougher time with this because what you want to do is you want to output a 1 if you've seen 0 or more X's. And if you haven't seen any X's at all, a Mealy machine can't output anything, right? Because it hasn't seen any input to consume. Whereas a Moore machine can right away say, yep, I've seen 0 or more X's, so I'm going to output a 1. I guess the way to get around that is say something like, with a Mealy machine, you put an epsilon in front, which means that you do now at least have a transition that you can follow. Something like that. So if you've seen 0 X's, you immediately follow the transition, you output a 1, and then every time you see an X, you output a 1. With a Moore machine, you can eliminate that first state. You can just have X/1, and then, you can just have a 1 on that first state, and then an X as a loop. Let me draw it out. Looks like that. So as soon as you start the Moore machine, you output a 1 because you've seen 0 X's, and then every time you see an X, you output a 1 again. Okay, but otherwise, Mealy and Moore machines are equivalent. And the reason why I chose Mealy machines, I think, is because they seem to make a little more sense if you're introducing this kind of from the start. I could have gone with Moore machines, but I did Mealy machines. So I think that's about all I've got for you tonight. Let's rehash all the examples we did. The first one we did was design a machine that can determine whether there's an even or odd number of something, and all you have is 2 states flopping back and forth. And then we did one that can invert the bits on a binary string by starting from the right-hand side and just flipping the bits as it goes. Oops, I'm sorry about that. And then we did one that does 2's complement. And again, it starts from the right-hand side and copies bits until it encounters the first 1. Then it copies that 1 and then flips the rest of them. Then we did one that could add 2 binary strings together by looking at successive pairs of the digits. So considering them in columns from the right-hand side. Then we could recognize substrings within a larger string. So instead of a regular expression outputting a yes or a no, yes, it does match that string, or no, it doesn't match it. This one outputs a 1 every time it sees 1. And then we found one that can recognize either an AB or a BA with 5 states, and then we were able to reduce it down to just 3 states. And then finally, just very briefly said that Mealy and Moore machines are actually equivalent. It's just that Moore machines, the outputs go with the states. Mealy machines, the outputs go with the transitions. So I think that's all I've got for you tonight. If there's any final questions, you can post them in chat. If I don't see anything in the next 30 seconds or so, then we'll call it a night, and see you next time. Yes, I will post all these notes here online on the class website. The question is, do you know any resources that show how to use regular expressions in practice? You know what, at our college, we do have some courses where regular expressions do come into play quite a bit, particularly if you're using something like the Linux or Unix command line. Then a lot of the commands that you use, a lot of things that you want to do are do things like search through files and find stuff. And in fact, we did an example in class where I had searched through a log file from a web server. That was an actual file from an actual web server. And those are the kinds of things you want to do. You want to find out, let's say, how many hits you had in the noon hour on March 21st. And so you could write a regular expression to find those lines out of the file and count them. So if you take a class in the Linux command line, you'll probably learn about commands like grep and awk and sed, and they'll sound like caveman speak, but that's what they're called. And they use regular expressions quite extensively. There's also some programming languages like Perl, PHP, Python, the three Ps, plus some of the others where regular expressions do factor into what you want, what as being part of the language. Perl in particular has regular expressions baked into the syntax of the language. So it's not, in other languages like PHP and Python, regular expressions are just put inside of strings, and then you pass them in through a regular expression parser to match against other strings. In Perl, the regular expressions are part of the language. So it's actually part of the syntax, which is really kind of neat because it can do things like at compile time, check the syntax of your regular expression and tell you whether you got it correct or not. And they can do all sorts of fancy things with Perl regular expressions, which are actually much more powerful than the regular expressions that we talked about using DFAs. Those Perl regular expressions can do things like match parentheses because they have the ability to count things and to do backtracking. So for every opening parentheses, they can make sure there's a closing parentheses. So wondering about programming and input verifications, very definitely. If you're doing web programming and you want, let's say you're having the user fill out a form and one of the forms is, type in your email address, you could do a very quick pattern match on that to make sure that what they typed in actually is something that looks like an email address, so it's got an @ sign in the middle and it's got some stuff on the right and stuff on the left. You do the same thing for things like phone numbers. Make sure that what they typed in, reasonably looks like a phone number. Zip codes. What else? Web addresses. So if you want to grab URLs out of a file, which is something that things like web crawlers like Google and Yahoo do all the time, you start with a web page, you go through the HTML of the page looking for URLs, things that look like URLs, and grabbing them out. And then those are the URLs that you go and follow and find the next web pages. And so you can build a complete map of the web by just starting at one web page and following all the links. But you need some kind of pattern match to go and find those things. That was using an online tool. You're right. We were using an online tool, but it was an easy and approachable way. Take the Unix class, take the the PHP class, and you'll do regular expressions a lot in programming, particularly for things like input verification and pattern matching on files. Any other questions? No, I don't see anything. So have a good evening, everyone, and I'll see you guys later.